I'm Dr. Narsinga, Professor of Physics, Dean Research and Development, Mlritm. So today we will discuss about Module 3, that is dielectric and magnetic properties. Now we will discuss about magnetic properties. So usually the magnetic properties is due to the electric field. So there is a electrons will move some one place to another place. So in that way, the magnetic field will be, magnetic moment will be generated. So a magnetic field is produced by an electrical charge in motion. Example, current carrying conductor or semiconductor. It will be produced or it will be induced to the magnetic field. So that type of movements of spin as well as orbital movements. So they will call it as a, due to that spin and orbital movements, the magnetic moment will be occur. So it will be described by, so already in childhood, means in lower classes, we will draw this magnetic induction lines. Just keep one magnetic compass and a magnetic magnet. So then we will, compass will be moving one place to another place. So we will draw that arrow marks. So it will be the inside and outside this flux will be going. So there in the north pole, it will be, the flux will be inside the material, and south pole it will be, south pole it will be inside the magnetic field, and north pole it will be outside. That means the magnetic field lines will enter into south and it will out from north. So in this way, the magnetic lines will be, magnetic lines of force, it will be looking like these curves. You can see here. So this magnetic properties defined like what is mean by magnetic moment and what is mean by magnetic dipole. So it's a magnetic dipole is nothing but it's a positive and negative charges where we electric dipole it's there. Similarly here, north pole and south pole, the equal and opposite magnetic moments, one is north and another one is south. So they will be distance between these two, it's some distance, then that type of moment we call it as a dipole moment. So the dipole, it contains north pole and south pole. So then the magnetic monopole is not possible, because we cannot cut the magnet. If you cut the magnet also, we cannot take north or south pole. It will be always with a smaller particle. If you make a small size also, there it contains north as well as south poles. We cannot, it cannot exist the monopole of magnet. That's is a property of this magnetic. And the two monopoles of strength, that is m plus 1 and minus 1, that is north pole is positive and south pole is negative if you consider. So the distance between these two is x, we can say. So then that magnetic moment is nothing but mu into magnetic moment into x. So that's a magnetic dipole moment we consider in terms of two you can see here, there is a two north pole and south pole. It's a distance between these two is a x. Then this magnetic moment of the magnetic strength or magnetic moment, we call it as a, that is related to the magnetization, that is a m, one pole magnetic unit into x, that is the distance between these two. So we can consider in that way the magnetic moment, we consider mu, that is m into x. So in this way we will calculate the values of these magnetic moments. So it's opposite and equal, we all know that. That is two dipoles. In each dipole there is a two magnetic poles, there is a north and south, it will be opposite. So then there is another important definitions, that is magnetic induction or magnetic flux density. So magnetic induction, how we can calculate the magnetic induction means the number of lines, where we saw in earlier slides, the number of lines passing through unit area. Number of lines passing through the unit area, we call it as a magnetic induction or magnetic flux density. So it depends on the area and number of lines. If the number of lines are more, you will get the more magnetic flux density. So that's in that way we will calculate the magnetic induction in terms of Webers per meter square. That's a unit of that magnetic induction, or we can consider as a Tesla also. So there is another unit, SI unit, that is Tesla. So Tesla means it's just 10 to the power of minus 10 to the power of 4 gas is equal to 1 Tesla. That is a unit of Tesla. It will be in terms of 10 to the power of 4 gas. So that's value will be like that. Usually in SI units, normal nowadays they use only Tesla, that unit. Okay. So magnetic field intensity at any particular point, if you required, so then the force experienced by unit north pole or south pole, it will be placed at that point. So that means the force due to that magnetic pole is called it as a magnetic field intensity. That magnetic field intensity is that's A is means amperes per meter, like that. So then it will require one unit area, that is called it as a magnetic field intensity. And another means usually in the magnetizations there is a permeability term will come. So like in dielectric materials, if the dipole moment, then they call it as a permittivity. Similarly here permeability. Permeability is in magnetism and permittivity in dielectric materials. So it's a magnetic induction is proportional to the applied magnetic field. If the applied magnetic field is more, so your magnetic field, that means if you have a very high magnet, then the force of lines will be more. That means magnetic induction will be more. So that means if the magnetic induction is directly proportional to magnetic field. So if the field is more, your magnetic induction will be more. So if the proportionality constant, they call it as a mu and h. That is, mu is called it as a permeability of the material. So usually permeability is equal to B by H. B is the magnetic field induction with the applied magnetic field. For my applied magnetic field, that is the magnetic field permeability of this any material. If any material, if you represent it's a magnetic, that permeability should be there. So that's a permeability definition. So usually all the magnetic materials will exhibit all the materials, it will exhibit some magnetic moment. So it may not be, it's only few materials are magnet, not like that. So all in a period, you can see here in this figure. So there is a periodic table in the number, means atomic number versus magnetic susceptibility. That is a value magnetic susceptibility. You can see there is a magnetic moments will be there in most of the all the periodic table elements, but some are maximum, some are high, some are negative, some are like that. So you can see there is a magnetic moment of lower atomic numbers. You can see it will value will be 5 into 10 to the power of minus 4, less than that. So you can see at particular this value, it will be maybe iron. So it will be higher value. That is magnetic moment. That is value magnetic susceptibility in terms of 10 to the power of minus 4. That's the value will be in terms of 10 to the power of minus 4. That's a small value will be there for all atomic number. That means in periodic table elements will contains all the magnetic moments, but some are will be positive, some will be negative, some will be very small, some will be like that. Depends on their behavior of magnetic material. Okay, that is some periodic table susceptibility. You can see, check here in this website, you can see the different type of materials, how the magnetic moment will be. So this periodic table, according to periodic table versus magnetic susceptibility. And why the magnetic moment will occur? Usually the magnetic moment, how it will be possible? So usually the magnetic material, if it is a best magnetic material, means there should be in a high, there is a means cells will be there, 1s2, 2s2, 2p6. So usually in outer cell, whatever the material, outer cell, there is a free electrons. If the free electrons are more, you will get the more magnetic moment. That's depends on these free electrons, you will get the magnetic moment. So that means these free electrons will move in around this magnetic material and around this nucleus. Depends on that movement, you will get the, these electrons are moving. Electrons are moving means you will get the magnetic field. In that way, they will be magnetic field will magnetic moment will be appears. In that magnetic moment, there is a three types of magnetism can arise in this type of materials. Usually the orbital magnetic moment, we can say there is a uh, p orbital, o orbital, s orbital, like that. The orbital to orbital attachment, that means oxygen, there is a p orbital will be there and s orbital will be there, 1s2 and 2p6, like that. These orbital moments or orbitals are arranged in a magnetic field. That type of magnetic moment also occur, that is due to orbital magnetic moments. That's one type of magnetism, that is magnetism phenomena, that is orbital magnetic moment of the electron. Similarly, the spin magnetic moment of the electrons. So one is orbital magnetic moment, that is p orbital and s orbital, d orbital, like that. The orbital itself is uh, means activating in that material to make the magnetic moment will occur. So that is called as a orbital magnetic. Usually this orbital magnetic moment will occur in some particular type of materials. I will explain later. So there is a spin magnetic moment of the electrons. Most of the magnetic materials, the basic phenomena is a spin magnetic moment of electrons. So usually in outer cell, if there is a more electrons are there, so the movement of that electrons is nothing but the magnetic moment, the spin moment. That is usually one electron is there. We can see at one spin is up and another spin will be down. That's according to Hund's rule. We have in each cell there is a two electrons is possible. So one is up and one is down. So then there is a no magnetic movement occur in this type of cells. So if the one cell is one electron, only one electron is occupied, another one electron. So like this. So then there is a adding of these electrons will get more magnetic moment. So that is occur in spin magnetic moment of the electrons. So in cells, they will occupy only single electron. So then only the magnetic moment will occur. If the outer cell is completely filled, then we won't get any magnetic moment. That is a very small magnetic moment will be there, depends on the material. So and another one is spin magnetic moment of the nucleus also participate in a magnetic materials. So nucleus also depends on the nucleus also the magnetic moment will occur. So this magnetic moment of nucleus and magnetic moment of orbital, it is usually in F F elements, that is lanthanides and actinides will be there. Lanthanum, praseodymium, gadolinium. These are the materials, rare earth materials, where these two mechanisms will be predominant. Whereas in a spin magnetic moment will predominate in transition metal ions like iron, manganese, cobalt, nickel. All these materials, the spin magnetic moment of the electron will be dominate. Whereas in rare earth materials, these two, that is orbital as well as spin magnetic moment also will be dominating in those materials, that is rare earth materials. So this origin of magnetic moment, there is a three types of magnetic moments where three types of mechanisms will be there to generate the magnetic moments, and depends on this magnetic moment value and this position and is positive or negative. Depends on that, the materials are classified into five types. Classification of magnetic materials in terms of magnetic moment. So first material, that is in general material, that is a diamagnetic material. One type of material is diamagnetic. Another one is paramagnetic material. So paramagnetic material. Then third one is ferromagnetic material. Usually these three general classification. In ferromagnetic material classified into another classification, that is antiferromagnetic and ferrimagnetic. These are the ferromagnetic material classification, but usually it will be classified as a five type of materials in magnetic materials. But there is a individual one, there is a different type of classification is there, but depends on that. It's depends on the material and how the magnetic moment will be. In general, the paramagnetic materials, it will be called it as a super paramagnetism, and some materials they call it as a means a spin glass behavior. Like that, there is a different type of materials will be classification will be there in magnetic materials. But in general, there is a 5 classifications, that is diamagnetism, paramagnetism, and antiferro, ferro, ferri. These are the 5 classifications of magnetic materials. Okay, let us individual we will study. What is mean by diamagnetic materials? Usually in diamagnetic materials, there is no permanent dipoles will be there. There will be no permanent north pole and south pole. There will be no magnetic movement will be there without any external electric field. So that's the first basic thing. If the magnetism arises due to change of the orbital motion of the electrons, usually in diamagnetism, there is a orbital motion will be occur. So this type of material, they call it as a diamagnetism. And here there is no magnetic dipoles in the absence of magnetic field. If you, this one is different at zero field, that is the magnetic field is zero. So if they apply the magnetic field, then the magnetic dipoles will be forming and it will move opposite direction of the magnetic field. So that's the behavior of these materials. What will happen if the magnetic field is applied? There will be no dipoles, permanent dipoles without any magnetic field. If you apply the magnetic field, the dipoles will form, and these formed dipoles will be movement will be opposite to the magnetic field direction. Because of this opposite direction, so that magnetic moment will be negative. Value will be negative and it will be very small value. Negative and small value. So that's means characteristic of diamagnetism. You can see here in the temperature dependent curve. So the temperature at x-axis is the temperature, y-axis is the susceptibility. You can see there is a diamagnetic material. It has shows the negative value. Here it will be 0, this one is positive and this one is negative. You can see there is a negative value and it is constant. That means temperature independent. Up to certain temperature, it will be temperature independent. That means a constant value. Okay, so this is the diamagnetic behavior, that is negative and small value. And it has materials where we can get this type of diamagnetism. So aluminum oxide, it will show the diamagnetic behavior at particular point, particular temperature. Copper also, gold and silicon and zinc. These are the materials. It will show the diamagnetic material, diamagnetic property. So you can see if you apply the magnetic field, the spin alignment will be opposite direction. So it will be oppositely, it will move in along the opposite to magnetic field direction. So these are the materials, and there is a in this phenomena, that means in diamagnetic phenomena, there is a superconductor also. It will occur. So superconductor also, it shows the diamagnetism. So there is a lot of applications of this superconductors because of this diamagnetism. There is a maglev train in Japan. There is a very huge application, and if there is a room temperature superconductors are occurs, that means the superconductor is one property is diamagnetism. That's why I am saying. So if the room temperature superconductors are occurs, then we don't fight for power, because the power once generated, it will be continuous, infinite time we can use that current, because there will be no loss of that power loss will be 0. So power loss 0 means you can use whenever you generate some 1 watt or 2 watts power, that power you can throughout the life you can use that power. So but if room temperature superconductor coming is very difficult. So that's another application of diamagnetism. What I am saying is that. So that's diamagnetism. It general diamagnetism rule is if value is negative and it will be temperature independent. Okay, that is diamagnetism. Similarly, what will happen in paramagnetism material? In paramagnetic materials, there is a dipoles will form without any external field, but these dipoles will be randomly oriented. So one spin of the dipole will be in one direction, another spin will be another direction. Like that, the magnetic dipoles randomly arranged without any magnetic field. If the magnetic field is applied, the rearrangement of these dipoles will occur. Due to this rearrangement of dipoles in a magnetic field, under the magnetic field, So then the magnetization, that is nothing but chi is equal to m by h. So if the chi will increase at lower temperature, so that's due to if the temperature is decreased, this magnetic moment also it will increase. This behavior of paramagnetic behavior. So this paramagnetic susceptibility, it follows Curie's law. So we all know that the Madam Curie. So that in her name there is a Curie equation is there. The magnetic susceptibility is follows temperature dependent magnetic susceptibility follows Curie's law. So that Curie's law is nothing but chi is inversely proportional to temperature. So that means chi is equal to C by T. C is the Curie constant. So this is the Curie constant. If wherever the paramagnetic material is there, this equation fits very well with that equation. So the materials are aluminum, whereas in diamagnetism, aluminum oxide. Okay, here paramagnetism, aluminum, chromium, molybdenum, titanium, zirconium, like that. So many materials are there where the paramagnetism will occur. So those type of behavior, we call it as a paramagnetic behavior. So here paramagnetism is small positive value and it will be inversely proportional to temperature. It is not independent of temperature. It depends on temperature. So that 2 points we have to mention. And there is a dipoles will be there, permanent dipoles. It with magnetic field, it will be reorient. Then magnetic susceptibility will come out. So that susceptibility is with decreasing temperature, it will increase. That's a property of paramagnetic material. Here another third characterization, that is ferromagnetic materials. These ferromagnetic materials, we know that everyone is well known, that is magnets we use frequently everywhere, like means whatever we are using in normal life, like sound boxes. In sound boxes also the magnets will be there, permanent magnets. Okay, so like that there is a magnets will be very friendly for our life. So is a permanent magnet. Here the dipoles, there is a dipoles will be without any magnetic field. There is a permanent dipole moment will be there in a ferromagnetic material. Without magnetic field also some magnetization will occur in that ferromagnetic materials. Okay, so this ferromagnetic material, it depends on the uncompensated spins. That is, in outer cell there is a number of electrons will be there, you will get the more number of magnetic moment. So this ferromagnetic material like iron, so you can see there is a 4s2 3d6. In this 3d6, actually in d orbital it has 10 electrons, but here it will be only 6 electrons. So that means the another 4 will be empty, that 4 will be valence electrons. So that due to these 4 valence electrons, you will get the magnetic moment. Okay. So and here in ferromagnets, usually the magnetic susceptibility, that are magnetic moment, is always positive and large value. Compared to diamagnetism and paramagnetism, this ferromagnetic material will have a large value of the magnetic moments, and it depends on temperature. So here the temperature dependence is not like earlier paramagnetic Curie temperature, but here it is, there is a modification of Curie equation, the Curie-Weiss law. There is a Curie-Weiss law. That's Curie-Weiss law contains C by T minus theta. This minus theta is extra compared to Curie's law. So this one is, they call it as a Curie-Weiss law. C by T minus theta. So this theta is Curie temperature, and this T is the absolute temperature. This C is the Curie constant. So here this type of observation in ferromagnetic materials, it obeys Curie-Weiss law. So examples of material like iron, nickel, cobalt, these are the best examples for ferromagnetism. You can see the curve with the temperature, how it looks to be. So you can see there's this one is 1 over chi value. Okay, so this one is ms, that is chi value. So nothing but chi value. So if the temperature decreases, the value you can see here. So the value will be increase and it will be saturated at lower temperature. So that means sudden increase of magnetic moment will occur at the particular point or particular temperature. That temperature they call it as a Curie temperature. This one is a Curie temperature. Below Curie temperature, it acts as a ferromagnetic material. Above temperature, it will act as a paramagnetic material. So only one material depends on the temperature. It acts as a para as well as ferromagnetic behavior. So that's a ferromagnetic material. You can see without magnetic field also, spins will be aligned, but some angles will be there. With field, it will be aligned perfectly along the magnetic field direction. Then at lower temperature, it will saturate. This is the ferromagnetic characteristics. And you can see in ferromagnetic characteristics, what we are saying, it's all are aligned at a particular direction or magnetic field direction. That is a ferromagnetism. And another part of ferromagnetism, that is antiferromagnetism. Antiferromagnetism means the surrounded, means the nearest neighbor spin will be opposite direction. If one is up, another side one, it will be down. So like that, you can see here, there is a manganese oxide. The one is oxygen and another is manganese. Manganese is the magnetic moment will occur. There's upper one is up, then another one is down, like that. You can see the one is up, one is down, like that. There is a one layer and second layer, like that. Depends on these layers also, this antiferromagnetism will be different. Okay, but now we just study what is the antiferromagnetism. Antiferromagnetism is nothing but the anti-parallel alignment of the spins will cancel each other and no net magnetic moment will arise. Because of this anti-parallel alignment, one is up, another one is down. So due to this anti-parallelness, so the net magnetic moment will be zero. So if when this type of behavior, we call it as a antiferromagnetism. And here antiferromagnetism also, the susceptibility is very small and positive value, and it is inversely proportional to the temperature. So whereas in ferromagnetism, you can see there is a T minus theta. Here it will be T plus theta. So usually Curie's law, we say it will be chi is equal to C by T plus or minus theta. This is a Curie's law. If the Curie's law for ferromagnetism, it will be negative, and it will antiferromagnetism, it will be positive. Like that, the Curie's law will be active for different materials. And positive value, small positive value, and inversely proportional to the temperature. So for example, MnO, that is the manganese oxide, how it looks to be. So this oxygen and manganese one, these manganese atoms will be anti-parallel to each other. So due to this anti-parallelness, there will be net spin magnetic moment will be zero. So one is positive means up means positive, down means negative means what? So positive, how much value is there? Negative, that much is cancelled out. Then it will net magnetic moment will be zero. So here you can see here there is a the curve looks to be the chi versus temperature curve looks to be like this. So at particular point, at particular temperature, the value of the magnetic material is decreased at particular value, that means the temperature, then it will be decreased. This decreasing trend is due to this anti-parallel alignment, because all are at a time and not anti-parallel. If all are anti-parallel, then it becomes zero. So but at slowly it will be alignment will be occurs. Due to that, it will be slowly decreasing. Where it starts decreasing the susceptibility, that point they call it as a Néel temperature. Here we call it as a Néel temperature. Whereas in ferromagnetism, we call it as a Curie temperature. Here it will be Néel temperature, because this alignment is developed by Niels Bohr. So that's why the temperature also, the transition temperature, they call it as a Néel temperature. That is a Tn it represents. So below Tn, it will be antiferromagnetic, whereas above one, it will be paramagnetic. Simple. Small increasing with temperature, it will occur. That will be similar like paramagnetic material. Whereas below Tn, it will be antiferromagnetism. So this antiferromagnetic materials. Last one, that is ferrimagnetism. So usually ferromagnetism and ferrimagnetism is a similar trend. The value, positive value higher, compared to ferromagnetism, it will be less. And it is also depends on the temperature. So the positive and large value, it is inversely proportional to temperature. You can see here there is a, if it is a ferromagnetism, all spins will be aligned and that spin and values will be same for all spin numbers. But here, due to there is a doping of some zinc and non-magnetic material, so that total spin alignment is different as well as the value also if different. If the value is same, like this spin value and this spin value is same, then it looks to be antiferromagnetism. But here what will happen? This value of the anti-parallel one value is a less value compared to parallel one. Then the net magnetic moment will be there. This net magnetic moment is less than ferromagnetic material. You can see the curve. If you can, I just redraw this curve. A is the ferromagnetic behavior and B is the antiferrom and this ferrimagnetic behavior. You can see the value is decreased, but the value is high only compared to paramagnetic or diamagnetism. So this value will be less compared to ferromagnetic behavior, and it is inversely proportional to temperature. And examples, best examples are zinc iron oxide, copper iron oxide, cadmium iron oxide. All these materials shows ferrimagnetic behavior. This is the classification of magnetic materials. So next one we will miss this classification, how we can see with susceptibility variation, reciprocal susceptibility. You can see the curve A. Curve A means it's an antiferromagnetic behavior. So where it will be minimum value, then it increase. So this point they call it as a Néel temperature. And second one, B is the paramagnetic material. Usually paramagnetic material, it touches the origin, that is straight line, it will be inversely proportional, that is 1 over chi versus temperature. If you draw the paramagnetic susceptibility, it will show that at origin, through origin, that is antiferromagnetic behavior. Whereas in ferrimagnetic, at minimum value will come, then it will increase, that is antiferromagnetic. Then diamagnetic, it will be only constant. So these are the three material variation of reciprocal susceptibility with temperature. That is antiferromagnetic and paramagnetic and diamagnetic. Whereas in ferromagnetic, it will be higher value. So we cannot keep all together in one picture. And you can see the permeability, that is nothing but magnetic moment. So how you can see the values, relative permeability of paramagnetic materials, usually in aluminum, it will be 1. Whereas manganese, it will also similar, just a small variation is there. But you can see the magnetic material, that is ferromagnetic material, like iron. You can see 2 into 10 to the power of 2. That means almost 100 times more than this paramagnetic material. So in that way, you can see in another material, there is a 4 into 10 to the power of 6. There is a combination of solid, cobalt, iron, boron, silicate. This one is acting as a permanent magnets. The value will be very high, 10 to the power of 6 times or 5 times nickel iron alloy. These are the alloys where we can use permanent magnetic magnets. So these are the magnetic classifications. So usually these points we took from these references. There is a engineering physics by Pandey and Holiday and Resnick also. It will be very old authors. So there is also important points will be there in magnetic materials. And a textbook of engineering physics. This for engineering students, they use this type of books. So thank you.